does that through policy that are developed by the community, and I can provide to that community a platform that help them define those policy. It's also specifically have the responsibility to coordinate the allocation and the assignment of the topmost level of IP addresses, autonomous system, and protocol numbers. That is another part of ICANN responsibility, although the IP address management happen at the regional level. For those of you who are already familiar with this environment, you know that there are 5 regional registries that are in charge of allocating IP addresses to network operator in each region. ICANN role here is to coordinate the allocation to those registries, regional registries, so that they can do their work. And there, again, it's important to mention that this is done via policy that are defined by the community again, and I can implement those policies only through the IANA function. And the last aspect of this specific part of its mission is to also foster collaboration with other body and organization to provide registry needed for function of the internet specified by protocol standards. That means anything that is defined in any standard of internet protocol that require putting in place a registry or a specific coordination. ICANN has also the mandate to work with those organizations to see how to manage them and provide them. Next slide, please. So in performing that mission, its bylaw says that it will act in a manner that complies with and reflects ICANN commitments and respects some of its core value. And what are those core values that drive ICANN work in general? And this applies with all the 5 different aspects I mentioned before. The first principle or value is for ICANN to preserve and enhance the stability, security, resiliency, and openness of the DNS and the internet. That means, although this is very specific to the unique identifier system, we quickly will realize that the DNS is one central element that connects those identifiers in a way or another. So keeping the management and the operation of the DNS and its relation to the internet secure, stable, resilient, and open is at the core, of ICANN mission as a principle. The second principle is to use an open and transparent bottom-up process to develop policy that are going to use to manage those resources. And that is where the community role is important, to participate, to contribute to those policy, and also exchange view with different actors, stakeholders, and interests in the community, so that policy that come out are consensus-based, but also take into consideration issue consideration from different parts. And ICANN has to work to always protect that transparency, that openness, and that bottom-up process in general. And last, because of the criticality of those identifiers, it's important that I can operate them in a very efficient way, pursuing excellence in all different aspects of its work, both fiscally, technically, and in others. So those are the 3 principles or core values that drive the whole mission in general. And as you can see, all those are focused on a secure and resilient operation of the DNS as a critical element. Next slide, please. I have two questions that I will come back to them very shortly. Sorry, I think this is the last slide that is in my presentation. So the agenda of what you are going to be talking about today has four components. The first one is introduction to the unique identifiers. That will give you through what we call unique identifier, how and where they are used on the global internet infrastructure, the scope of their use, and where they are linked to ICANN. Then we will dig down into the DNS by giving you an overview of how the DNS work, what are the different components of the DNS, and how they interlink with each other. The third part will now show what are the some of the threats that the DNS face on its day-to-day operation, so that we can understand where to act to protect the DNS in general. And then the last part will be the policy development process. As I mentioned, one critical role responsibility of ICANN is to provide a platform that is open, transparent, and bottom-up oriented for a community to build policy, design, and develop policy that will allow an efficient and effective operation of the DNS through allocation at the root level. So at the end, you will have those, the global overview of those different components. And as I mentioned again, as policymakers, that should be something that you keep in mind when discussing or thinking about policy that will strengthen the internet infrastructure in your different country, that helps you promote the digital economy locally. Knowing this will help you set policy that does not put at risk the stability of the internet, as we say today, but rather contribute to strengthen their resiliency locally, so that resiliency supports your economy. Next slide, David. I think that is the last in this session. Yes. So I will let you continue with David and Nicholas, but I will have a quick look at the questions that are in the Q&A pod here. How can digital transformation be better handled in the term of policy? Okay, is it possible to share what constitutes policy in the context of the presentation? Okay. I will start with the second one. The last part of this presentation is going to address the policy development process, so you can see, concretely what we are talking about policy. But I can give you a simple example. Policy. There are policies that define, for instance, what goes into the root zone from ICANN perspective, and that is what allow stuff like IDN to be able to be in the roots, for instance, to allow characters that are not ASCII character to be represented in the roots, is an emanation of a policy that ICANN defines. So anyone today can request ICANN to delegate a domain name that is not ASCII in the root. So that is an example of policy. There are many other policies that are related to general name, related to some technical compliance here and there. The first question was, how can digital transformation be best handled in terms of policy? I think that is a question that has a lot of ramification, and I will answer simply by saying that each context, each local context will dictate and drive the policy for digital transformation, because everyone is not starting from the same place, and the notion of digital transformation is about integrating the digital world into how the economy works in general, so to make life of people globally easy, but also provide the economical framework, tool, and stability, confidence that is needed for innovation to happen, and use for the internet or digital tool in general to support the economy. So it is a transformation slowly from the economy we have known in the past, that is more physical, to something digital. But that something digital has to be has to lie on a very stable infrastructure, a very stable, I would say, a component that secure, give confidence into the digital. So where to start from will vary, and how to do it also will depend on the reality, the local reality. I hope I've touched on those two questions. I don't see other question. I mean, the last one was responded to by David already. Okay, any further question, any further comment before we move on to the next part of this presentation?
I don't see any. I think we're good there.
Good, thank you. Passing now to David.
Oh, thank you so much, Adiel. All right, we're going to move on to the next section about introduction to unique identifiers. Before we do so, what's really cool about hearing from Adiel is not only is he a vice president at ICANN, but he's also a member of the Internet Hall of Fame. Adiel is considered an internet pioneer in the continent of Africa, and he really moved Africa from a non-connected state to a fully connected state. And it's really an honor to hear from him. And for me and Nicholas, it's really an honor to get to work for him. So let's talk about unique identifiers. What we're going to talk about is MAC addresses, Internet Protocol addresses, IP addresses. I'm going to introduce this concept of autonomous system numbers, and we're going to talk about domain names. And after we introduce these four different identifiers, we're going to talk about how these are managed in a way that hopefully helps put it all together. So the internet is importantly a mesh of networks, okay? This is what it actually looked like in 1977 when it was very early. And each one of these is a site somewhere on the internet, and a bunch of machines and a bunch of routers about how things are connected in different geographies. But this is what the internet looked like 46 years ago, 45 years ago. This is more what it looks like today. We could zoom out this picture, and it would have 40 or 50,000 of these bubbles. And it's all these different independent networks that connect to each other many different ways, creating a mesh. And this is where identifiers come in. The operators of each of these independent networks agree to communicate. They agree that they want to exchange information, data, across the wire. And it can be done not just on physical wires, of course, it can be done wirelessly. And we agree to do so using protocols like TCP/IP and UDP. And when you have these protocols, you need to identify the machines that are communicating. And the computers that do these calculations need numbers to do this. So what we say is the networks use identifiers to name or number individual computers, which we call hosts. And it's this identification process that allows us to enable internetworking, the internet. So let's start with MAC addresses. MAC stands for Media Access Control. These are 48-bit identifiers. That means there are 281 trillion addresses. There's an example. You've seen it on some of your devices. It's hexadecimal. 0 through 9, A through F, and that's what it looks like. Every network component, like a Wi-Fi adapter, an Ethernet adapter, your Bluetooth, your mobile device, 4G, 5G, whatever it is, every one of those is given a MAC address. Each network component is giving a MAC address, and it's done so when it's manufactured, when it's actually created, when it's built. And that MAC address is burned into the network adapter by the manufacturers. In fact, the first 24 bits, the first half of each MAC address, is actually used to identify which manufacturer has created the item. You know, Intel, Apple, Dell, Huawei, whatever it is. Unlike everything else we're going to talk about today, MAC addresses are actually permanent identifiers. They remain constant. They don't change when a device switches networks. When you have a laptop and it's on your home network, and then you go to school and it's on your school network, and it's in your company, it's on your company network, the MAC address of the network adapter being used never changes. It's constant. So the internet runs mostly on Internet Protocol, IP. And IP requires every host that connects to the internet to have an address. And so we call it an IP address. And we have two types of IP addresses. The one most people are familiar with is called IP version 4, IPv4. This is a 32-bit address space with 4.29 billion addresses. And a good example of it is 192.168.0.1. But 4.29 billion addresses actually isn't very many. We would have run out of that a long time ago because there's way more than 4 billion devices, and there's way more than 4 billion people. So back in the 1990s, we expanded the address space with IP version 6, IPv6. This is a huge address space. It's 128 bits, 340 undecillion. I don't know what an undecillion is, except it's a really, really, really large number, okay? And this is what it looks like, as you can see on the screen. I'm not going to read that out, but it's 8 what we call quartets, groups of 4 digits, and they're actually hexadecimal. Each digit can go either 0 through 9 and A through F, okay? So we have this concept of public IP addresses and private addresses. We can also refer to this as a locally unique address and a globally unique address. So what does this mean? Okay, so the IP address, when you're on your local network, whatever device you're on right now, it might be assigned a private IP address. And that means it's unique only within the subnet of your local network. I'm on a laptop right now. I'm inside my home outside of Washington, D.C. in the United States. And the router that I'm connected to has assigned my laptop a private IP address. And no other device on my network has that address. But it's only unique to this network. My router itself that connects to my ISP, it has a globally unique IP address, or what we call a public IP address, because it needs to communicate with hosts all around the world. So it needs a unique address that everybody can get to. Your company that you work for, the school that you go to, the ISP that you have in your home and at your work, can assign a private IP address to your device and perform what's called NAT, Network Address Translation, which allows many different devices to share a single public IP address for the purposes of conservation. Next is this concept of autonomous system numbers. We refer to those, abbreviate those as ASNs, autonomous system numbers. So an autonomous system is a group of networks that comprise a single administrative routing domain. My ISP in my area here in Washington, D.C., is a single autonomous system comprising all of the homes and businesses it connects. And it's identified with an autonomous system number. The number space is, again, 32 bits, which means there are 4.29 billion ASNs. And the way you can think of it in your mind is think about AS numbers as a way to identify the networks you visit. If you go to Google, any site on Google, Google Earth, Gmail, google.com, you may find it's part of a single AS. In this case, www.google.com is part of AS 15169. ICANN, the organization we work for, is part of AS 40528. And the purpose of AS numbers is used for routing. It allows routers to do the calculations it needs to find what networks each IP address is housed in. Our final unique identifier today is domain names. www.icann.org, our website, is hosted behind the IP address 192.0.32.7. But I don't want to have to memorize that, right? And humans don't naturally memorize that very well. I go to a lot of websites every single day. I can't and don't want to memorize their IP addresses. So we use the DNS to map semantic names that are easily understood by you and me to the IP addresses that are easily understood and necessary for the computers. What's cool these days is the domain names are not limited by language or by alphabet. We can use technology called Unicode to translate all words and all letters into machine-readable ASCII strings. And that allows internet users in almost any language in the world, using any alphabet, any script in the world, to participate in the DNS, in your local language, in your local alphabet. So we've got all these different identifiers. Well, how are they managed? Well, the MAC addresses are managed by the IEEE, the Institute for Electrical and Electronics Engineers. The IP addresses and autonomous system numbers are managed by the RIRs, the regional internet registries. In Africa, that's AFRINIC. In South America and Central America, that's LACNIC. In the United States and Canada and parts of the Caribbean, that's ARIN. In much of Asia Pacific and the islands in Oceania, it's managed by APNIC. And in Europe and parts of the Middle East, it's managed by the RIPE NCC. And I'm going to show you a map of this in a couple of slides. Domains, like top-level domains, .com, .net, .museum, .edu, a country code, .bj in Benin. These are managed by what we call domain name registries. The individual domain name registrations, www.icann.org. The .org is managed by a public interest registry, a registry called Public Interest Registry. The domain name itself is managed by a domain name registrar, where individuals and businesses can manage their specific names. All of this has an umbrella. It's managed under the umbrella called the IANA function. The IANA is the Internet Assigned Numbers Authority, and it's a very old concept, and it predates much of the modern internet. The IANA function manages domain names, it manages IP addresses and autonomous system numbers, and it also manages protocol parameter registries. In a way, what you can think of the IANA function is it's responsible for the operational aspects of how we coordinate this system of all these different identifiers. And it does so by implementing policies that are defined by you and by me as part of the community. The IANA function today is performed by a subsidiary of ICANN called PTI. PTI stands for Public Technical Identifiers Incorporated. It's a company incorporated in the United States. It's a wholly owned subsidiary of ICANN, and we all just call it the IANA. So let's talk about how IP addresses are distributed. All the IP addresses have a central registry, which is at the IANA. And then the IANA has distributed over the decades all of the IP addresses, IPv4 and IPv6, to each of the 5 regional internet registries as we've defined them. The regional internet registries then give out the IP addresses to internet service providers and large organizations like universities, corporations, community networks, all the different, what we can sort of think of as top-level network providers. They get their IP addresses from one of the regional registries, the one that's in their region. If we own a company in Egypt, then we get our IP addresses from our local registry, which I believe is AFRINIC. Then the businesses and the individuals who connect to these ISPs get their IP addresses from the ISPs. So it's very hierarchical. The IP addresses start with the IANA, they go to the regional registries, then they go to our different ISPs in different formats, and then they come to our individual devices. Here's the domain names. It's a little bit different. Each of the top level domains, the .com, .net, .aero, .us, .uk, .ru, .cn, each of those is handled by an individual registry. Okay, and a registry contracts by any business rules that they define with individual registrars to sell those domain names. The registries are typically in the business of running the registry so that everything works, And the registrars are in the businesses of selling the domain names to you and to me and to our employers and our schools. And we are called registrants, an English word that means we're the ones who have the registration of www. Whatever our domain name is, okay? The registry-registrar relationship is contractual. There are some requirements that are put in there by ICANN policy, but it's a willing, voluntary business relationship between two companies, one the registry and one somebody who wants to be a registrar. And then when you and I register domain names, we also have a contract. We have terms of service that we have to abide by, terms of use, between us and our registrar. Registries also have contracts. They have contracts, as we said, with the registrars. Registries also have contracts with ICANN that dictate how the registry has to run. So in a nutshell, that's what unique identifiers are. That's who manages them, and that's how they're distributed. I'll pause here for just a moment to see if there are any questions. After this slide, my friend Nicholas is going to take over, and he's going to present about DNS 101. He's going to really teach you how DNS works from the ground up. I don't see any questions, so I'm going to stop presenting. And Nicholas, when you're ready, go ahead and present your slides, and up to you.
Thanks very much, David. I'm going to share a screen now. Okay. So is the screen showing, David?
It is, and I can see
Yes.
it.
Great. So I have a kind of virtual laser pointer here. Okay. So what are we gonna go through now? The idea is to go through, as David mentioned, to go through DNS and how technically works, how DNS works from a technical perspective. We are going to go through the basics of DNS. There could be, you will find quite a lot of information in this section. There are some slides that we are going to go through them very fast, and other slides that we are going to give a little bit more of explanation. The idea is also for you to keep this presentation afterwards, so you can go back and use it as a reference. So again, feel free to ask any question in the Q&A during the presentation. I will try to answer all of your questions. So this is what this presentation is for. So let's go. Names and numbers. David already talked about this. We have devices spread all over internet are assigned a unique identifier in order to reach them, in order to be able to exchange information with those devices. We assign a unique identifier we call IP address, whether it is an IPv4 or an IPv6, or both of them in the ideal actual case. Why we use names instead of IP addresses? When we want to refer to some specific device, for example, we want to access a server that hosts a web page. We want to access that web page. We don't use the IP of the server. We normally use the name of the server. For example, we want to go to the ICANN web page to find some information about DNS. So we type www.icann.org in our browser, and then the browser will end up, pulling all that in web page and display that web page to us. So we use the name. We don't use an IP addresses. Why is that? Because we people normally tend to be better at remembering names instead of numbers, sequence of numbers. So someone realized that, and they say, okay, let's refer to devices and to internet resources in general with names, using names, and then let's have a means to translate those names into the actual IP addresses, which is the one that we need at the end, is the one that we need for accessing that information. So that's the main idea and the main rationale behind the DNS existence, right? we have names, easy to remember. Then we need addresses to exchange information with devices. Then we build a system that translates from names to addresses. That's what the DNS does. Okay, and the process of resolving those addresses, finding those addresses corresponding to those names, is the what we call name resolution process. Okay, so what's the DNS? DNS is a distributed database. We always see it as a distributed database. So not all information is concentrated in one place. Not all information is administrated by only one organization or company. So all the information stored in the DNS database, it's spread all over the internet, and there are many administrators for that. We are going to go through that in a while. So if we talk about devices that participate in that DNS resolution process, we are going to talk about mainly two kind of devices, servers in this case. We are going to talk about what we call resolvers, and we are going to talk about what we call name servers. So resolvers are the ones that send the queries. So they get the queries from the end user, let's say, from us. We type www.example.com or .icann.org. That's the query. We want to know the IP address that corresponds to that name. So we make a query to the DNS system and say, okay, I want to know the address, the IP address corresponding to this domain name. And the system will end up eventually giving me or telling me that IP address. That is what resolvers does. They get the query from the final user and find the answer, and finally they give me back the answer. And then there are the servers that we call name servers or authoritative servers, that are the ones that actually hold all the information, all the DNS information, all that correspondence between names and IP addresses is stored in these name servers. So resolvers send queries, name servers answers those queries with the corresponding IPs for the names we are asking for. Okay, and then there are some optimizations built into the DNS systems. We are going to talk a little bit more about this in some minutes. Those kind of optimizations are what we normally call caching. That is to improve the performance of the whole system, of the overall system, and then what we call replication. That is to provide mainly to provide redundancy and to distribute the load. So this is kind of instead of having only one server with all the information, for example, one name server holding all the information for the DNS, which is, it's impossible to do that. But instead of having that, yeah, we have that information distributed all over different name servers. We are going to go through that also in a while, and also each of those servers can be replicated. So we can have more than one replica of each server holding the same information in order to provide more redundancy and in order to distribute the load. If I have 2 or 3 or 4 repositories to get certain information from them, it's that way I can send the query to any of those servers, because all of them have the same information. Any of them can answer me, and the response will be exactly the same. So I can balance the load and send some queries to one of them, some other queries to another one, but by that way I distribute the load. Okay, so how's the DNS namespace? The DNS, it's organized in terms of architecture, or in other words, which is the architecture for the DNS system. The DNS system, as we mentioned before, it's a distributed database that it's structure in what we call an inverted tree. This inverted tree you see here, it's an inverted tree because the root of the tree, which is normally at the bottom of the tree, here it's at the top. So the DNS has the root at the top, and then all the logs and branches, go down to many levels. So this is where the database starts in the root here, which is normally referred with a dot. It hasn't got a name. It's the only node in that tree that hasn't got an actual name and is represented only by a dot. That's the root. And then we have levels, what we call levels in that tree. Each of those levels have different nodes that we call domains. Yeah. So this is the first level. This is the second level. This is the third level. So the domains that are within this first level are called first level domains. The domains that are within this second level are called second level domains, third level domains, and so on. Okay. Then what are the rules for assigning names to these nodes? So what are the rules for assigning domain names? The rules are mainly these three. You can use letters, you can use digits, and you can use hyphen. Okay, and initially the standard was designed so as basically all names were written in using ASCII code, but then there is this introduction of what we call universal acceptance, that is or internationalized domain names, which is that allows us to be able to write domain names in different languages. So for example, in Spanish, that we have for example, my name Nicolas actually have a symbol over the A that is not able to represent only using ASCII code. So it was introduced this universal acceptance or internationalized domain names, that it's a means to be able to write or define domain names in different languages. So the DNS supports that, actually supports the writing in any language. Just have to go through a process to develop and implement those characters or those letters, and you will be able to write any domain name in any language. Okay. The maximum length of a domain name is 63 characters. That's by design. And domain names are not case sensitive, so it doesn't matter if you write it uppercase or lowercase. Okay, so we said that we have the structure of the DNS is an inverted tree with a root at the top, and then we have levels, what we call levels: first level domains, second level domains, third level domains, and each of those levels has or may have many domains. Okay, in this example, we have in the first level, we have the domain coffee, we have the domain com, we have the domain UK. So in the first level, there are all the well-known domains, .com, .org, all the country codes assigned domain names, what we call CCTLDs, or country code top level domains, which is the a domain that is assigned to each country in the world. .uk, .uy for Uruguay, .us for United States, whatever country. Each of the country has a domain name assigned, and that's also a top level domain. Yeah, so top level domains are mainly of two types. Let's say the country code top level domains and the general top level domains that normally we refer to we normally refer to them as CC-TLDs for the country code and GTLDs for the general top-level domains like .com, .org, etc. Right? Okay. So what's a domain name then? So a domain name is a label, a name assigned to some node at some level. For example, this node here has the name example, right? This is the example domain. But you see here that there's a potential issue. If we say, for example, let's take this one, www here. If I say, okay, www domain, which of these three I'm referring to? Am I referring to this? Am I referring to this or to this? Because the three of them are called the same, have the same label, www. So in order to be able to refer to a unique or a certain domain within a certain position in that tree, we have to tell what we normally call the full qualified domain name. It's not only possible to refer to a domain by only mentioning the label for that node. We have to mention all the way back up to the root. That is the fully qualified domain name. So again, the fully qualified domain name is to refer to a certain domain, but by mentioning all the way back to the root. How we do this? We normally do this by writing or speaking the name of starting with the name of the domain we want to refer to, then the next domain, the parent of that domain, then the parent of that, and so on. And we separate all those labels by a dot. Example, if we want to refer to this, we will call it the full qualified domain name for this domain will be www.example.com. We normally do not write nor mention this dot, the one that refers to the root, which is at the end of the full qualified domain name. But you have to remember, you always keep in mind that that's there, whether we mention it or not, it's there. So the full qualified domain name, again, for this is www.example.com. The full qualified domain name for this mail domain will be mail.example.com. The full qualified for this www, which is different from this is a different domain because it's in a complete different branch of the tree. It would be www.foo.com and so on. Okay. Okay. So at the end of this explanation, a domain, it's a node, will be a node. Yeah, we already talk about a domain name. Okay, a domain, when you normally refer to, sorry, as a domain, is a node and everything below that node. So all the tree starting from that node down, it's what we normally refer as to domain. Okay, so if we are going to refer to com domain, we are going to be talking about this domain name, this label for this node, and all the tree under this node. So what is the com domain? The com domain is comprised of this label and all of these that are here. If another example, we are going to talk about the example domain. If we are going to talk about this domain, the example domain will be comprised of example and www and mail. So the line will be here, and these three will be the example domain. Okay, so that's a domain. Okay, again, to recap: domain name, a label assigned to a node; domain, a node, and all the tree down starting from that node. We're talking about domain names and domains. that's how for how the DNS architecture is built and how DNS is designed. But how about administration? Because all of this, it's going to be a database where we are going to store information. Which information? Mainly the IP address corresponding to a name. A lot of IP addresses corresponding to a lot of different names. So in order to administrate this, we are going to also spread the administration among different entities or different organizations. Yeah, so not a single organization will administrate all the DNS. So how can we distribute that administration? Well, in order to distribute that administration, we create what we call zones. So a zone, it's a division for administrative purposes. Okay. How this works? This is again the DNS architecture with the root at the top, and then all the domain, the examples we have in the previous slides. But now we are going to divide this into different administrations. So there's going to be an entity that will administrate the root zone here. Then we in this example we created a zone for this domain, a zone for this domain name, a zone for this domain name, and a zone for this domain name. You see here are 4 zones, 4 different zones in the first level in this example, of course. Then we create a zone, but to administrate these 3 domain names, or if you want to mention, to say it in a simpler way, all the domain, the example domain in this example, it's gonna be administrated by the same entity or the same organization, right? So we enclose all of this into a single zone. Then we create a zone to administrate the bar, this bar domain, and then we create a zone to administrate this few domain. These divisions are can be whatever you want. So a zone, it's delimitates an administrative section of the whole DNS system. You can assign zones as desired, and what that will end up is each of the administrators of a certain zone will have the authority for all the information that it is stored in that zone. So all the information related to a certain zone, it's the property, let's say, of the zone administrator. Okay. So to recap again, up to this point, we have talked about domain names, which is the label assigned to a certain node in the tree: com, coffee, example, www, mail. We have talked about domains, which is a node and all the tree under that node. And we have talked about administrative divisions that we call zones in the DNS. Okay. Here it says delegations create zones. So how do we assign these administrative divisions to different entities? Okay, so the root, it's administrated by one entity. The actually responsible for the content of the root zone is IANA, the one that David already mentioned. Then there's a delegation for the first level domains. Yeah, you see here in this example, coffee is delegated to one entity to administrate. .com is administrated by a different entity. .uk is administrated by a different entity. In this case, .uk it will be administrated by some assigned entity from United Kingdom, because this is a CCTLD, and so on. In this example here, all the example domain here, it's administrated by one entity and it's delegated. .com delegates the administration of this into a different entity. .com also delegates the the administration of bar domain into a different entity and the administration of foo domain into a different entity. So each father can delegate the administration of its childs to different entities, creating new zones. So each time you delegate the administration of a child of you, you create a new zone. You assign this entity the administration of all that new zone. Okay. So now this is the owner and the one that's authoritative for the information in this new zone. Okay. All right. Going back to where we start, names, name servers, answers, queries. A name server authoritative for a zone has complete knowledge of that zone. That is, it can provide a definitive answer to a query about the zone. So we mentioned that the one that runs, that administrates each of these zones has the authority for all the information and is responsible for all the information within that zone. Okay. And as we mentioned also, each of the zones should have multiple authoritative servers that the server that holds that actually holds all the information for this zone won't be a single server. We normally have, or we should have, more than one server for storing that information. All those servers will have the exact same information. That gives us redundancy and that allows to spread the load among all those servers. Okay, it's think as this as if you have, for example, you are a content provider. You provide videos for people to see using internet, and you have a server with all the videos stored there. Yeah, that is a single server with all the information. So that represents a single point of failure. But what you can do is to make copies of that server, having, for example, 3 or 4 servers. All of the 4 servers will have all the same videos, so people can access any of those 4 servers to get a video. So you spread the load, and you also have more redundancy, because in case of one server fails, people won't notice it, because they have other, in this example I'm telling, we'll have other 3 servers to go to get the same information. Okay. So how do we keep zones data in sync? We mentioned that if a zone administrator has multiple copies of the same server, there has to be a means or a way to synchronize those servers, because all the servers within the same zone, all the authoritative servers for the same zone should have the same information. So all those servers should be synchronized in terms of information, should have the same copy of all the information. There's a protocol for that. Fortunately, there's a protocol built into the DNS protocol suite, let's say, that is meant for synchronizing the content of an authoritative server, yeah, of the server that holds information for a certain zone. And that protocol will be in charge of maintaining the same information in all the servers. Okay. Normally we can have an architecture, or we can implement this by having what we call a primary server, and then a couple of any number we want of what we call secondary servers. So normally that is easier for the administrator to deal with all the management for that authoritative server. Think of this way: if you have to administrate 3 servers, and you have to make sure that the same information is in the three of the servers. Okay, you can do it. That the worst way of doing that is to copy the information in server number 1, then copy the same information in server number 2, then copy the same information in server number 3. But each time you change any of those, we have to also replicate that change in the other 2 in order for the 3 to have always the same information. As I mentioned, there's a protocol for that So you don't have to administrate or to manage that infrastructure that way. So you only define one server. This will be my primary server. All the changes I do, all the information changes I do it in that server. And then the protocol will make sure that the other servers, 1, 2, 3, or any number of servers I have, they are going to be the secondary servers, and they are going to automatically copy and synchronize all the time with that primary. So I only change the primary, and then the others are changed by the protocol automatically. That makes the administration far easier. Okay. Normally, also the transfer is initiated by the secondary. So the secondary will basically the protocol, the synchronization protocol works at the secondary level. The secondary server will each X minutes will carry the primary server and say, okay, is there any change in the zone file, or is there any change in the information? If the primary server say yes, there's some change, the secondary will fetch the new information, the updated information, and will be always in sync with the primary. Okay, the DNS standard specifies the format of DNS packets that are sent over the network. That is what we normally call wire format. So that's the format that the DNS standard defines for exchanging DNS information. There's a format to make a query, and there's a format for the authoritative server to respond to that query. Yeah. So that's what we call wire format, the format of the information that DNS servers exchange. Basically, as we mentioned, those servers are the resolver, the server that the recursive server, or normally called resolver, which is the one again that gets the query from the client and goes and finds the answer by querying the authoritative servers, and the authoritative servers that are the ones that hold information for a certain zone. Okay. Recall that every node has a domain name. A domain name can have different kinds of data associated with it. We mentioned that a domain name, normally the most important associated data with a domain name is the IP address. We normally want the IP address corresponding to a domain name to be able to access that specific device in the internet. But it can have other kinds of data associated with that domain name. Those different kinds of data associated with a certain domain name is what we call resource records, are stored in those resource records. I like to see this as imagine the DNS as a warehouse, as a huge warehouse where we store information. Okay, that warehouse is not centralized. There's no a single facility in a single place. It is spread all over the internet. The administration, it's also not centralized. It is spread all over the internet in what we refer as zones. So the administration is also spread or distributed, and the data is stored in those zones. So imagine those zones as the shelves in a warehouse facility, right? You put the information in those shelves. So each time you want information, you will have to look up in one of those shelves. You will first will need to find the facility where that information is, then go into that facility, find the shelf where the information is, and get the data from that shelf. Resource records are like boxes in each of those shelves. Any of those boxes can store different types of information. One type of information is, for example, the IP address corresponding to a certain domain name. Another type of information could be the email server corresponding to a certain domain name. Another type of information could be a text record to store any arbitrary, any text we want to associate any text string to a domain name, or any other information we want to associate with that domain name. All those information associated with a domain name are stored in those boxes that we call resource records. So there are different resource records for different kind of data. And a zone file, if you look at a zone, inside a zone, you will find different resource records that are different pieces of information associated with a certain domain name. Okay, so a single domain name can have different resource records associated with that. Okay, these are the most common resource record types. What we call record type A, that stores the IPv4 address corresponding to a domain name. What we call the quad A record. The quad A record stores the IPv6 address corresponding to a domain name. We mentioned, for example, www.icann.org or .example.com. We want to access the web page, the ICANN web page. The ICANN web page is stored in a web server that it's run by some ICANN staff group, and they assign that server. They assign an IPv4, but they also assign an IPv6 to that server. So where's the IPv4 corresponding to the ICANN web page server? Stored in the A record. So in the A record for the www.icann.org, it's where the IPv4 address is stored. In the quad A record for www.icann.org, it's where IPv6 address for www.icann.org name it's stored. And these are other common resource record types. NS, which is the name of an authoritative name server for a certain domain name. This is each domain name server has a name. So the physical server, when you store all the zoning, all the information for a certain zone, has also a name. That server, that's a machine that has a name. That is what we refer to the NS record. SOA, CNAME, MX. MX is the record type that stores the name of the mail exchange server for a certain domain. For example, if you want to send an email if you want to send me an email, my email will be something@icann.org. But that @icann.org, it's an email server, it's not a web server. So you will want to know the IP address associated with that email server in order to be able to send me an email. If you want to do that, you first need the name of the email server, and then you need the IP address, and that's the name of that email server is the one that is stored in this resource record type called MX. And then we have many other resource records. Actually, if you go to this page here, http www.iana.org/assignments, blah blah blah, you go to this place and you will find all the actual resource record types that are actually defined by the standard. At this moment, as of November this year, there are 88 types of records defined or allocated. Okay. This is an example of how this information is stored, or it's written into a zone file, which is the file that has all the information, the authoritative information for a certain zone. We can go very fast through this, but mainly the record for that, the line for that record in this example, the domain name example.com has an IPv4 associated address, which is 192.0.2.7. And also example.com has an IPv6 address, which is stored in the quad A record, which is this 2001, DB87. Okay, so this is the box that stores the information for IPv4 address. This is the box that stores information for IPv6 address, and this is the way that that information is actually, defined in the zone file. Resolution process. So we talked about how's the DNS architecture. We talked about which types of information we store in that architecture, and we also talked at the beginning. We mentioned that the whole idea of this is someone is willing to know the IP corresponding to a domain name. So how this works, how I end up knowing the IP for a domain name. That is the resolution process. That's what we are going to look up now, quite fast, but in order for you to understand how it works. So let's go to the explanation. Before going to the resolution process, let me very quickly mentions how it is, how it works. Sorry, and a few things that we will need to know before going into the process itself. This starts with a client willing to know the IP for a certain domain name, right? I type www.example.com in my browser. The browser needs the IP address for that web server in order to get the web page. So it queries the DNS system. It sends a query that says, I want to know the IP address for www.example.com. The client will send that query to a resolver. We mentioned that we can think of DNS system as a huge warehouse when we store information. So in order for the clients not to have to go themselves to look for the information, we have the resolvers. The resolver will look for the information, will look at the information for me, and then it will give me the answer. So I send my query to the resolver. Then the resolver will go through all of those warehouse facilities looking for the information, will find the information, and it will bring it back to the client. So you have the client, you have the resolver, that is the one that looks for the information, and you have the authoritative servers that are actually the warehouse facilities that stores all the zone information for each of the domains. Okay. So how does this process works? How do you start the resolution process? The client will send the query to a resolver. How does the client know which resolver to send the query? Well, the resolver is normally assigned by the ISP, by your internet service provider. The one that provides you internet connectivity normally provides you with the IP address of a resolver. They say, okay, in case you want to resolve any name, in case you want to make use of the DNS resolution process, you want to make use of the DNS system, send your query to this resolver. So you already know the IP. Your ISP already told you which IP to send the query to. That is the resolver. So you already have an assigned resolver, let's say. So you, the client, send that query to that resolver. Okay, now the query is in the resolver. So the problem is at the resolver level. So how the resolver gets the answer for that? Because the resolver doesn't have any information itself, that it doesn't store any information itself. It just looks for the information, and then it gives it to you, to the final user or the client. So the resolver will need to start looking for that information into this huge database called DNS. Where to start? The resolver will always start at the root level. It will first query a root server, a server that holds the information for the root zone. Okay. Let me go back to the DNS, to this example. So the resolver will first query this, the root server. The resolver will send to some root server, the resolver will send the query. Hey, I want to know the IP for this domain. That is where everything, all the resolution process starts, okay? So in order for the resolver to be able to do that, to send the query to a root server, it has to know the IP address of a root server, right? You don't want the name of the root server, because if you have the name of the root server, in order to contact the root server, you will need the IP address, okay? And then in order to know the IP address, if you have the name, you need the DNS system, and then we fall into the egg and the chicken problem. So all resolvers have to know the IP addresses of the root servers, okay? How resolvers know IP addresses of the root server? That's easy. They came already hard-coded into the resolver code. So when you run a resolver server, resolvers already have all the IP addresses of the root servers stored in memory. So they know where to start the resolution process, okay? And I've already mentioned all the IP addresses of the root server. So there's no one single root server. We mentioned that each zone, we are talking now particularly about the root, each zone, the root zone, it's another zone, okay, of course, has a replication. So there are many servers for the same information. That's also valid for the root. There's no a single root server. There are many root servers. All of those root servers have the same information, and all the resolvers have all the IP addresses corresponding to all of those root servers. How many root servers are there? Okay, there are 13 root server IPs, and this is something that we should always remember. It's the same to ask how many root server IPs are compared to how many root servers are there. No, there's a complete difference between how many root servers are there and how many root server IPs are there. And this is where things get a little bit, or may get a little bit complicated, but let's go step by step. There are 13 IP addresses for assigned to root servers. When the standard was defined, they assigned 13 different IPv4 addresses, then they assigned 13 different IPv6 addresses to the same 13 IPs that were distributed. So initially, it is true that there were 13 root servers, one with a single and unique IP address, okay? Those servers were also assigned a name, which begins with a letter, A, B, C, D, up to M. These are the 13 servers. And then the name goes rootservers.net, okay? They have their IPv4 address and they have their IPv6 address. Okay, so each resolver has this information already stored in the resolver. This is actually the only information the resolver initially have, the way to find the root servers. So the resolver can send the query that got from the client to any of these 13 servers. All of those will have the same information. So I can send the query to any of those, and I would eventually get the same answer, no matter which of them I'm reaching, okay? The administration of the root zone is complicated. There are two organizations cooperate to administer the root zone contents. Those administrations are ICANN, more precisely IANA operator, which is the PTR that David already told you, and VeriSign. IANA is the owner of the content for the root zone, let's say. The one that managed the information and the responsible for the information of the root zone, not all the DNS. We are talking about only the root zone. The responsible for all the information of the root zone is the IANA. And then VeriSign is what is called the root zone maintainer. So IANA, the responsible for the information, for the content of the root zone file, will send that information to VeriSign. And VeriSign, which is the root zone maintainer, is the responsible for distributing that information, distributing that same information to every other root server operator. So now we have a root zone owner, let's say, which is the IANA. We have a root zone maintainer, which is VeriSign. And then we have those 13 root zone operators. Those operators operates the servers that store the information that then the resolver will look at. So I was telling you that VeriSign is the responsible for sending that same information to all of the 13 root server operators. Okay, those 13 servers, you remember that I told you that 13 IP addresses were assigned to 13 different operators, to 13 different servers at the beginning, are managed by only 12 organizations. Things get a little bit more complicated. If you say that there were 13 IP addresses assigned, why are you telling now that there are only 12 operators? Well, because one operator operates 2 of those servers. Okay, so these are the actual operators of the 12, the actual 12 operators of the root zone servers. VeriSign, University of Southern California, Cogent, University of Maryland, NSAA, Information System Consortium, ISC. There's another one administrated by NetNode. There, and you see here, server with the name J and server with name A are both managed by are both run by VeriSign. So VeriSign runs 2 servers. That's the reason because why there are 12 server operators for the 13 IP addresses. There's one that is VeriSign that operates 2. So VeriSign here has also 2 roles at the same time. We are talking about the role for root zone maintainer, which is the responsible for distributing the information that came from IANA to the root server operators. And VeriSign is also a root server operator. So it's the root server maintainer and also a root server operator. And as you see here in this list, there's also a server that is operated by ICANN that we normally call IMRS, ICANN managed root server. So ICANN also has 2 roles in this ecosystem. One role is to be the owner and the responsible for the root zone content, the data, and also it's a root zone operator. Okay, what is important here is that all these 12 operators are not responsible for the content. They cannot change, they cannot do any change to the root zone content. They are just operators of the servers. They get the information, the copy of the root zone from VeriSign. VeriSign got it from IANA, and just put the information of the servers that they run, that they manage, and that's all. That's their job, their task, what they do. They just put the information in the servers, and of course run the servers, which is not a minor task, right? You have to run the physical servers. You have to run all the copies. We are going to go through that in a couple of minutes. And they operate the root servers, but they are not responsible for the information of the root zone. So back to the question of how many servers, how many root servers are there then? 12 operators. That means that are only 12 root servers out there? No, actually, as you can see here, there are thousands of servers. There is I don't know if it's here is a number, but up to today, if you go to this page, rootservers.org, you will see the amount of root servers that are actually operating in the whole internet. That's one. Let me, because I don't see the number here. Well, okay, let me just go very fast to that root servers.org, to that site to check for what's the actual number as for today. I see here it's 1,475 instances operated by the 12 organizations. Okay, so these 12 organizations we mentioned operates in total 1,400 something servers. So how many root servers are there? 1,400, over 1,400 servers operated by these 12 organizations. All those servers, all those root servers have exact same information. So any resolver in the world can query any of those 1,400 something and to get the same exact information. Okay, back to the resolution process. This is where our DNS 101 presentation will end. How does the resolver gets the information to give to the client? Recall that in our example, we want to know the IP address corresponding to www.example.com, right? So our client sends the query to the resolver. The resolver was assigned by ISP. The client already knows the IP of the resolver, so it can reach the resolver and send the query. Now the resolver has to find the answer. We mentioned that the resolver will first query some root server. Any of those 1,400 root servers will be carried by the recursive resolver. By the way, you may wonder how, if there's only 13 IP addresses assigned, why you are, I'm saying that there are 1,400 some servers all over the internet. Well, that's why they use a technique called Anycast that will enable a root server operator to have multiple copies of the same root server, all of those copies sharing the same IP address. So again, all the copies of a certain root server, take one of those 13 root servers, all of the copies of that root server will have the same IP. So there are hundreds of root servers that have the address for root server A. There are hundreds of servers that have the address for root server B, and so on. If you sum up all of those, you will end up with that 1,400 something root servers. Okay, so the resolver will send the query to some root server. The root server has the answer for that. Does the root server know the answer, the IP corresponding to www.example.com? No. The root server only knows who are the ones that have the information for the first level. Remember that the root is the parent of all the first level domains. So it will only know the answer for the first level domain. So the root server won't give the answer that the recursive server is looking for, but it will give the recursive server an answer that will allow the recursive server to find the first level domain server that will make it, that will get it close to the final server that has the information that the recursive server is looking for. So again, to recap this, the root server won't have the answer, but it will tell the recursive server, okay, I don't have the answer, but you should ask this to the .com first level domain server. Okay, and this is the IP address for the .com first level domain server. So now the recursive resolver has the IP for the .com domain server. then the recursive resolver will say, okay, let's ask the .com to see if it has the answer. The recursive resolver sends the query to the .com server in this example. Which query? The same. Hey, .com server, I want to know the IP for www.example.com. Do you have it? And the authoritative for the .com says, no, unfortunately, I don't have that. But I am the parent for example.com. So I know which is the IP address of example.com server. You should ask him. Okay. Then the .com server answers or replies to the recursive resolver query with the IP for example.com server. The recursive resolver sends the exact same query to the example.com server asking, hey, example.com server, I want to know the IP address for www.example.com. Do you know the address? And in this case, example.com server is the one that holds the information for www.example.com. It's the authoritative for that information. So finally, the recursive resolver finds the authoritative for the query it's looking for. The authoritative for example.com will answer the recursive resolver with the information it was looking for. In this case, it will say, yes, I have that information. This is the IP address corresponding to www.example.com. The recursive resolver gets the answer, says, oh, I find the answer that the client was looking for, and gives the answer to the client. The client gets the answer, now knows the IP corresponding to www.example.com. It will pass that to the browser, and the browser will be able to finally get the data from the server that contains the web page. For this case, that was www.example.com. Okay. What other task does the resolver, the recursive resolver, does in this case? Well, other from giving the answer to the client, which is its main function, it will store the answer. The resolver will store the answer in memory for a while, for a period of time. In order to what? In order to, in case the same client or any different client asks the same, suppose that another telephone or another PC just ask the same recursive resolver the same question, which is the IP address or www.example.com. The resolver already looked for that and already has the answer because it stores that in memory for a certain period of time. So that way, the resolver won't have to go again through all the resolution process to get the same answer, because he already get it, the answer. He already has the answer. So as the answer is in memory, the recursive resolver will get that query, which is the same, and say, okay, I already know that because I asked it that before and I find that information before. So the recursive resolver will get that information from its memory and give it back to the client. That way it will speed up the process because, again, it doesn't have to look up for the answer again through all the DNS ecosystem. Why that information is stored only for a period of time and not forever? Because that information can change. The authoritative servers for any correspondence can change the IP address, can change the domain name. Maybe the domain name no longer exists or the IP address of the server changed. So in order for the resolver to know if any of those information that has in memory changes, it has to store only for a period of time. After that period of time, the information will be deleted from the recursive resolver memory. And if someone asks the same again, it will have to look for it again. So it will have to go through all the process we mentioned again and find the answer again. Okay. That recourse or that activity for the resolver of storing the information, temporary storing information in memory, is what we call cache. So resolvers does cache. What is cache is that is storing the answers it gets from the authoritative servers for a while in memory. After that period of time expires, it deletes from memory, and if someone asks the same, the resolver will have to look for it again, going through all the resolution process again for that domain. Okay, and that's all that was meant for you in this DNS 101 presentation. These slides that remain here explains exactly what we already mentioned. The case that someone asks again the same question: what's the IP address for example.com, and the recursive, as the recursive resolvers already knows the answer for that, it will go. It will either fetch it from memory, or it can happen that, as in this example, it can happen that the question is not exactly the same. You see here, it's not www.example.com IP that the client wants to know, but ftp.example.com, and it sends the query to the resolver, and the resolver, of course, it hasn't got this in that information in memory, because the resolver knows www.example.com, but not ftp.example.com. So we will have to start looking for that information, but the resolver already knows who is the authoritative for example.com. So it won't answer the root, nor, it won't carry the root, nor carry the com server. It will go straight directly to the example.com server and say, hey, now I want to know the ftp.example.com. And the example.com will answer that, and the recursive resolver will give the answer to the client, and also store that answer for ftp.example.com into the cache. Okay. Questions here, up to here. Can a domain name apply different from the name of the company? Is there any countries adopt this approach? Can domain name apply different from the name of the company? If I'm getting this question right, yes. The short answer is yes. I mean, there's no relation. Mainly, there's no relation between the domain you are trying to register, the domain you are trying to buy or to get as a client, or to registry, with the company you work for. You can register any domain as long as it's not taken by anyone else. If the domain is free to take, you can take it. You can register. It doesn't care if it's actually, if let's say if Coca-Cola.com wasn't taken by Coca-Cola, potentially I could register Coca-Cola.com. Probably, if I do that, if I on purpose register a domain that it's not already taken by a big company, but it refers to a well-known big and global company as Coca-Cola. Coca-Cola will start a process in ICANN, probably saying, hey, this domain was registered by another one, but you know, I'm Coca-Cola, and someone else is trying to appear as if as if he's Coca-Cola, and you have a process to try to go. I mean, you have to go through a very long process, but there's a way to I don't know how to say this in with the correct words. Maybe David can help me with this, in case someone else registers a name that you think that it should belong to you. You can start the process to end up either getting that name or having the other one give you or transfer the name. But the answer is yes. You can register any name as long as it's not taken by anyone else. Okay. If there's no further questions, I'll go back to you, David.
Okay. If you could stop sharing, please.
Sorry. That's it.
Okay. We're running short on time, unfortunately. We only have about 18 minutes left. So I'm going to skip to the last section, talking about ICANN policy and how you can participate in shaping the future of the internet. ICANN policy is at its base a bottom-up consensus-driven policy development and advice. It's development work that's at the core of the ICANN mission. ICANN is a ecosystem. It's made up of three components: the ICANN community, the ICANN board of directors, and the ICANN organization. The ICANN board reviews and adopts policies. It directs the ICANN organization to implement them, and it oversees the performance of the organization. The distribution and decentralization of power and responsibility works with a strong system of checks and balances. As the ecosystem, everyone holds each other accountable. So we've got two parts to our community here. One is about making policy, and one is about providing advice. Policies made by our three supporting organizations. These supporting organizations represent different communities: IP address communities, generic top-level domain communities, GTLDs, and country code top-level domain communities, CCTLDs. And while these three supporting organizations directly make policy, advice comes into the system from 4 different advisory committees. The advisory committees are made up of representatives from government and international treaty organizations, from root server operators, from internet security experts, and from internet end users. So we have 3 supporting organizations in the ICANN community: the Address Supporting Organization, the ASO. The ASO has 15, they have a council, an address council. It's 15 volunteers, 3 each from the 5 regional registries. And the ASO works on global IP address policy. Another supporting organization is the CCNSO, for country code names. And this, the CCNSO consists of CCTLD managers. And these managers agree to be members and participate in what's called the CCNSO Council. And then there's the generic name supporting organization, all the other TLDs that don't directly represent a country code. The GNSO consists of what's called CPH, the Contracted Parties House, which is the registries and the registrars, and then non-contracted parties. These are commercial and non-commercial interests that have, again, interest in domain names, and the overarching GNSO Council. For these supporting organizations, they each have their own processes to support and facilitate bottom-up and consensus-driven policies. For the GNSO folks, you can see it on the screen. They identify the issue, they scope it, they initiate a policy development process by forming a working group and creating final reports, which they then discuss. And then eventually, when they've reached some form of consensus, they send it up to the ICANN board, which consults the community, consults the governmental advisory committee, and then they vote on the final report recommendations. And that's how policy is made if you are in the generic name supporting organization. And there are similar processes for the CCNSO and for the address supporting organization. Talking about these 3 supporting organizations in a little bit more detail, the GNSO is responsible for developing and recommending to the board substantive policies relating to how GTLDs work, how they operate, how they're formed. The GNSO Council manages the policy development process for the GNSO. This is what the GNSO looks like hierarchically. There's this council at the top, which has 18 members. It has constituencies like the Commercial Stakeholders Group, which itself is made up of the business constituency, the intellectual property constituency, and the internet service provider and connectivity providers constituency. It has the registries stakeholder group. It has the registrars stakeholder group. and also a non-commercial stakeholder group, which is made up of the non-commercial users constituency and not-for-profit operational concerns constituency. So each one of these groups represents constituencies, groups of people who have common interests. And many of these are open to the public to join to help the GNSO Council form policy for the GNSO. And they do so through a policy development process. An issue is identified. It can be identified by the GNSO and its council, maybe the ICANN board, or maybe an advisory committee identifies the issue. And then the council considers if this issue will result in consensus policy. And if yes, they issue some reports. They work with the staff to do some public comments on those reports. And then they do what's called a final issue report. The GNSO Council considers the final issue report and decides whether or not to initiate a policy development process. And if yes, it develops and adopts a charter. The policy development process involves forming a working group, writing final report, deliberating what the final report says in its recommendations, and submitting it to the ICANN board for ratification. Then there's the CCNSO. The country code name supporting organization, just like the GNSO, works on global policies, but these are only related to country code top-level domains. They have a very similar policy development process. An issue is identified, figure out if this is within scope. If it's in scope, which is defined by the bylaws, we can initiate a policy development process, which includes developing reports and putting them out for public comment. Lots of different consideration touch points here: initial reports, public comments, final reports, getting input from the GAC. And then there's voting. And the CCNO does voting a little bit differently. They do it in multiple stages. They start with the CCNSO Council. And if they adopt a report, they then make recommendations to the members. And then the members can then separately vote to approve or not. And if they do approve, then the CCNSO Council submits the final report with its recommendations to the ICANN board for ratification. But we know with policies that affect CCTLDs, we always have to keep in mind that individual national laws for each country always remain paramount in our mind. Finally, on supporting organizations, there's the address supporting organization. And the ASO is governed by an address council, which has 3 members from each of the regional internet registries. And they work on global policies related to IP addressing. Again, this is very similar to what you've seen, where we figure out that there is an issue. This can often come from an individual RIR's community. And if it's going to be a global policy, it raises up to the ASO. And then the ASO works on a policy proposal facilitator team to determine if the global policy proposal requires specific IANA function actions or different outcomes. When a policy is created, it has to be reviewed by each of the 5 RIRs. All 5 RIR communities have to debate and discuss and eventually ratify a policy for it to become a global address policy. And when they do, the ASO then submits it to the ICANN board for ratification. So those are the 3 supporting organizations. There are also 4 more very important parts of the ICANN policy ecosystem. And these are also very often open to the public so that everyone can participate. These are the at-large advisory committee, which we call the ALAC. The ALAC voices the interests of individual internet users. It's for the end users. It's for everyone who uses the internet, who doesn't formally get represented at ICANN by another constituency. There are 15 members on the ALAC Council, 2 from each of the regional at-large organizations, and 5 appointed by the ICANN nominating committee. It's supported by over 200 at-large structures around the world, and by all the many hundreds and hundreds of volunteers who give their time to support the ALAC. I've referred a couple times today to the GAC. The GAC is called the Government Advisory Committee. This is one of the ones that's not public. Members are appointed to the GAC by their countries, and they become official representatives of their countries to the GAC, which then provides advice to ICANN and the ICANN board and the ICANN policy development process. The GAC concentrates particularly on how policies and national laws and international agreements that exist can interact with the technical policies that we discuss in the ICANN ecosystem. Another non-public, partially non-public advisory committee is called the RSAC. This is the Root Server System Advisory Committee. And the committee itself is made up of 2 representatives from each of the root server operators, appointed by the root server operators. But they've also formed what's called an RSAC caucus, which is a bit more public. Members of the public who have good credentials can sign up to be part of the caucus and help the RSAC in its work product, in developing its work streams and doing the work of the RSAC in creating policy recommendations and written advice and papers. One more advisory committee we have is called the SSAC, the Security and Stability Advisory Committee. And it advises ICANN on matters related to security and integrity of the unique identifier system we've been talking about today. I'm not going to go through this slide because there's a lot on it, but similar to the supporting organizations, each of these advisory committees has its own advice development process, kind of like a policy development process, except it's for providing advice to ICANN, to the ICANN board, to the ICANN staff, and to the ICANN community. So as we're reaching towards the end of our session today, you can participate in policy and advice development. You do so by looking at the different constituencies, the different working groups, and the different communities, and figuring out which one aligns with what you want to accomplish or where your expertise is. You observe their work by listening in on calls, by attending webinars, by subscribing to mailing lists, and then becoming part of that community and giving your input. And another very important way for everybody to participate at ICANN is through the public comment process. All policies, all ideas that are to become policies go through a public comment period. And everybody in the world, organizationally or individually, is allowed and encouraged to submit their thoughts during the public comment process, during the period of what they think of the policy being proposed. And that's a very important way to provide direct input into the policy development process of any supporting organization. So that's the end of the webinar slides. I see a couple of questions. I'll try and answer them really quickly. What is the safety profile of the ICANN storage in the multi-stakeholder community considering the operator's risks? The safety profile. I'm not sure what the question means. Adiel or Nicholas, do you understand the question better than I do?
No, maybe this refers, David, Nicholas here. Maybe this refers to what happens if with the how does ICANN manage the risk of any operator, for example, becoming inaccessible or whatever. If something happens with an operator, how ICANN reacts to that? I mean,
well, it depends on the type of operator we're talking about. You know, ISPs generally run independently of governance organizations like ICANN. If you're talking about one of the RIRs, you know, the RIRs work together, both as a group of RIRs in their own umbrella organization and with ICANN to mitigate some of the risks, to mitigate some of the problems that can happen. For domain name registries and registrars, there are actually some contractual safeguards. There's some guardrails to help protect data. Yao, I hope that answers your question. If not, please resubmit. Chris asks, I seek clarification on the relationship between Afrinic and ICANN with respect to getting an ASN, most especially for internet service providers in Nigeria. Okay, Chris, that's a good question. The Afrinic community develops its own policies that indicate when an ISP in the Afrinic region can qualify for an ASN and when they cannot. Those policies are created in this bottoms-up multi-stakeholder environment within the Afrinic community. And then the Afrinic staff carry out those policies by publishing the rules on the Afrinic website and in the policy manual that say, okay, if you want an ASN for your ISP, here's what you need in order to qualify. And if you can't meet these qualifications, then you can't have them. These aren't related to ICANN. ICANN does not trump or oversee how Afrinic policy is made and how the Afrinic staff carry out that policy. So the question of how to get an ASN for an ISP in Nigeria is working with the hostmaster staff at Afrinic to learn what the qualifications are and make an application using the paperwork that they asked you to. How can DNS attacks be prevented policy-wise? Very good question. Generally, the ICANN community tries to develop policies for registries, registrars, and registrants to protect against types of DNS attacks. For example, we require that registries support DNSSEC. DNSSEC is a technology. It's a set of protocols which can give you better protection against man-in-the-middle attacks and give you assurances that when you load up a site, if there's DNSSEC validation taking place, that it's really the site you intended to go to and not a different site masquerading as that site. We use the policy process to require that different operators in the ICANN ecosystem adopt some of the security guards that exist technologically to better protect all of us. Okay, it is the top of the hour and we have reached the end of our session together. Thank you all for coming. Jamal, it's over to you.
Yeah, no, thank you so much, David, Adiel, and Nicholas for today. A lot of information packed into 2 hours, definitely meaningful. And I do say thank you and from the USTTI